Yeah, so our scenario was that you have 10 people on basketball courts, and you have to make two teams out of them. And our first case was for 10 choose 5 and 2. And we said, pick 5 people for one team, which is 10 choose 5. And then you have to divide it by 2 because the teams aren't labeled, so you're like over counting. You have the same 5 people on one team versus the same 5 people on the other team, the same thing. And then our second case was you're a team captain and you have to choose the other 4 people on your team. And we said that was 9 choose 4. And since we got the same, since we got both these answers with the same case, we said that they were equal.
Okay, team captain chooses 4 other people for their team, where 9 available. Can you elaborate a little bit more on the overcounting part?
Yeah, so like if we had 4 people, so let's say if we're on the same team and we're on the other team, we would overcount if so like if they were picked, then we would be what's left. And if we were picked, then they would be what's left. So you're kind of picking the same teams in 2 different ways.
Okay. Any questions on that? Points of confusion? Cool. Great job. So yeah, so this happens to be the, so there's this question on the homework that I just passed out, and it was the same question twice, essentially. There was the table question, and then there was the basketball question. So I just wanted to go over this and give you an opportunity to practice your combinatorial proof skills. All right. Also before you sit down, how many ways can fan meet the requirements to run all these laps?
For the first one, we got 3 ways, and then for the second one, we also got 3 ways.
Okay, I agree with you on 3 for the first part. I disagree with you on 3 for the second part. For 3, this ends up being, so 8 is 1 plus 1 plus 1 plus 4. So it has to be, each day has to be at least 1. And then as we go, we'll just write them like in increasing order, because it could be like 4 plus 1 plus 1 plus 1. And because the order for addition doesn't matter. So let's just like simplify the way that we write it. So that's a possibility. Or 1 plus 2 plus 3. So we take 1 from 4 and bring it to the previous day. Or is 1 plus wait, no. I'm missing a 1. 1 plus 1 plus 2, 2, and 2. That's our solution for 8. If she has to run 7 laps over 3 days, I'll tell you that that is 1 plus 1 plus 5. And 1 plus 2 plus 4. Or 2 plus 2 plus 3. Wait, no, I'm missing 1. 1, 3, and 3. Okay. So the answer for the other part of that was 4. Questions? All right, let's return to our seats. Thank you very much. All right, so it's time to go to poetry class. I am writing a limerick, or I didn't write this limerick, but we're reading it. There was a young lady named Bright who traveled far faster than light. She set out one day in a relative way and returned home the previous night. So when we're in poetry, we can label the last syllable of each line with some letter. And so, for example, we have bright, light, day, way, night. And so we would label this with the rhyming scheme A, B, B, A. Right? Sounds familiar? So now my question is, how many different 5-line rhyming schemes can be employed with 2 sounds? So I've got 2 possible sounds, 5 possible lines. Turn to your neighbor. What do you think? All right. Anybody have a guess? Yeah,
Well,
we have a guess of 12. How come?
we said there's 6 ways to do the A's, and then there's 5 ways to do B's. Or sorry, 2 ways to do the B's. And then you will apply them.
6 ways to do the A's. How do you get 6?
For the first line, you have 3 options. And the second line, you have 2 options. And then the last line, you have 1 option. So we said 3 times 2 times 1.
With the first line, you have 3 options.
Yeah. Like you have, there's 3 possible lines that end with the A sound. And then, like if you were to pick one to be the first line.
I see. Okay, so this is, yeah, I see the confusion. So the initial example is a limerick, which has 3 A's and 2 B's. I think the question is asking for 5-line schemes in general, not restricting, like, there has to be 3 A's and 2 B's.
Okay.
So, like, we've got A and B, and we've got 5 possible lines. Don't care, like, that there are 3 of one and 2 of another. Yeah.
But we had 5 line options and we have 2 choices between A and B for each line.
That's a good guess.
We could do like line 1 is either A or B, line 2 is either A or B.
So I agree with the idea. But the way that, so this section in the book is a little bit like, it's a little bit tricky. It's a little bit like we've decided to throw our rules out the window, but not really. We're not really throwing the rules out the window. So the answer that the book has is they're like, okay, first let's look at where, so let's consider A. Let's look at where, okay, I'm gonna erase these. So I've got room. So when A appears once, so like thinking of how many times does this pattern occur, there's only one possibility. 1, 2, 3, 4. And then there's similarly when A appears twice. There now we get into 4 choose 2. So there's one possibility where A appears once. And this is so because of the way that the question is framed of 5-line rhyming schemes, we're assuming that it doesn't matter which line A ends up on, just that A appears once. So when A appears twice, we've got 4 choose 2. When A appears thrice, we've got 4 choose 3. Nope. Wait. Hold on. I'm confusing myself. No, sorry. This section is confusing. Okay, so when A appears twice, we can fix it to the first position. And then there are 4 choices for the second position of A. So if A is in the first position, and then we've got 1, 2, 3, 4 possible choices for the second one. When A appears 3 times, it's 4 choose 2, which is 6. For when it appears 4 times, it's 4 choose 3. And then in no patterns can A appear at the end of all 5 lines, since the sounds A and B must each appear at least once. So 4 choose 3. Here's 4. And so we sum all these up and we get 15. So the reason this is kind of different from usual is that the lines where we assign the pattern are kind of indistinguishable. We don't really care on which line the pattern ends up, right? So the lines are indistinguishable. This is equivalent to something called a Stirling number of the second kind. This is what the book calls it. So a Stirling number of the second kind implies that there's a Stirling number of the first kind, but we're not going to get to that. And this is, we denote it S of n comma k, which is the number of ways to distribute distributing n distinguishable objects into k indistinguishable boxes. So n distinguishable objects into k indistinguishable boxes. So 5-line rhyming patterns, we have not defined which line is the first, which line is the second, and so on. And there's an important caveat with no box being empty. Okay, so that's the Stirling number. The way that we find this number is not so intuitive. We don't have a nice fancy equation like we do for combinations or permutations. We do have a theorem to help us do that. So this is theorem 11.9, which says Stirling numbers of the second kind satisfy the following equations for integers k and n, where k is limited as being between 2 and n. So the first part is the Stirling of 1 and 1 is equal to the Stirling number of the second kind as n and 1, and also n and n, and all of these are 1. The second shortcut we have is the Stirling number of n and 2 is 2 to the n minus 1 minus 1. And if we've got some number n and n minus 1, then that is just n choose 2. And then we've got pretty much all other cases where the Stirling number of n and k, to choose k, to put n distinguishable objects into k indistinguishable boxes, this is equal to n minus 1, k minus 1, plus k times n minus 1 and k. Okay, so our equivalent for the limerick problem is we've got 2 rhyme schemes and 5 lines of poetry. So this is, we don't care which line it goes into. It's right. So we don't care which line this goes into. And so to do that, we find that it satisfies the second option, which is 2 to the 5 minus 1 minus 1, which is 2 to the 4th is 16 minus 1 is 15. Cool. All right, so the next thing is the question that I asked for the warm-up, which is secretly a questions on how to partition an integer. So if we've got an integer n, so for an integer n and k, we define a k partition of n to be an expression of n as the sum of k positive integers, assuming it's a sum, so the order is irrelevant. And so we denote it as lowercase p of n comma k. As the number of k partitions of n. And so for the example where Fan is running laps around her school's track, we found that so we've got lowercase p and we have to run 8 laps in 5 days. So 5 partitions of 8, the number of those is 3 because there's 3 possibilities. If she has to run 7 laps in 3 days, it should be a lowercase p, there's 4 ways of partitioning 7 into 3 integers. And so we said that that number is 4. Similarly, there's a way to do that. Let me add a new page. So we've got another theorem kind of like that. That's a lot. I don't want to write that. I don't know that you want to write that either. Let's screenshot that and put that in here. That's this guy. Okay, so here's how you calculate that. So we've got different cases on what number we're looking at. So if we have to run 8 laps in 8 days, that where we have this increasing requirement where each day you have to run at least the same amount of laps as you ran the previous day. This is the same as if we wanted to run 8 laps in 7 days, which is the same as if we wanted to run 8 laps in 1 day, which is the same as if we wanted to run 1 lap in 1 day. That's all 1. So that's the first category. If we want to run 8 laps in 6 days, we have 2 options for that. If we want to run 8 laps in 2 days, we can calculate how many ways we can do that as the floor of 8 over 2. Lucky for us, 8 over 2 divides evenly, so it's just 4. And then we've got a case for if n is a multiple of 6. But case 4 gives us the general example. And so for case 4, if we want to figure out 8 laps in 5 days, this is equal to the number of ways to partition 7 laps into 4 days, plus the number of ways to partition 3 laps into 5 days. How many ways can we partition 3 laps into 5 days where we meet all these requirements? if we're assuming positive integers, we can't. And so this just ends up being 0. Because it's not possible to do that. And so this is equal to number of ways to partition 7 laps into 4 days. And does it meet any of our criteria? Not yet. 7 laps into 4 days is the number of ways to partition 6 laps into 3 days plus 6 minus 3 is 3 to 3. Okay, good news. I know what P of 3 comma 3 is. I know that's 1. And then 6 comma 3 gives me this equals 3n squared. Which is 3 times 6 squared. That feels wrong. Okay. I'm going to be honest with you. I don't necessarily care what these numbers are. I just care that you are able to write it in this form. So if you're able to figure out that this sort of problem fits into an integer partition, then you can write this is P of something comma something. And then you can leave it at that. Because these numbers are hard to calculate because we don't have a nice equation like for combinations or permutations. All right. From there, we've got these sort of 4 cases where we're talking about, so the question that the book says is, given n objects and k boxes, how many ways are there to place the objects into the boxes? So this is an overly broad problem. And so there's 4 cases that kind of make it more specific. So the cases depend on whether the things are distinguishable or indistinguishable. So if the items and the boxes are distinguishable, then we've got 2 cases inside there, which are, can things be empty? Can the boxes be empty or can they not be empty? And so this is assuming not empty, and the second case is assuming empty. So for case 1, we've got the Stirling number of n and k, and then because the boxes cannot be empty, and so from there we just have the items are distinguishable, and so we need to multiply that by k factorial to get them all in there. However, if the boxes can be empty, so this is like if we don't need one of the lines to have a rhyme scheme, then we just the number of ways that we can distribute all 5 items into all 3 boxes is k to the power of n. And so this holds for each of the things in this table, where A is can things be empty? So if the items are distinguishable, but the boxes are not, so that's case 2, then for if the boxes can't be empty, that's just the Stirling number. If the boxes can be empty, then we sum the Stirling number to figure out how many things are in there. This is a little bit different from if we say that the box is allowed to hold at most one object, then we get into permutation land. And so this is it's different, where we're assuming that maybe a box can hold more than one thing, but the box just can or can't be empty. If the boxes are distinguishable, but the items are not, then this is just a combination. So if the items can be if the items cannot be distinguished, but the boxes can, and we can't have an empty box, then that's n-1 choose k-1. Otherwise, it's n plus k-1 choose k-1. And then if the items are indistinguishable and the boxes are indistinguishable, so that's like we have to run some number of laps on some number of days, and I don't care about the order in which I run the laps, and the laps themselves aren't distinguishable in any way, then that falls into the partition of integers. Okay, let's look at an example. So a bus has 30 passengers and will be making 6 stops on its last route of the day. In how many total ways can the passengers choose the stops where they will disembark? Okay, what are the items? What number corresponds to the items? Yeah.
30.
Yeah. So that's n. And then how many boxes? 6. Because it's the last route of the day, so everybody's got to get off the bus. And so which case do we think this falls under? Turn to your neighbor. Do you think we can distinguish one or the other? Okay, can we distinguish the passengers? I think so, because each passenger is a different person. Can we distinguish the stops? Yes, because like if you're taking the bus from here to BART, it matters if you get off at St. Mary's versus at the library versus at BART. The stops are distinguishable. So that puts us into case 1. And so then we have the question of empty or not empty. So could no one get off at a stop? Yeah, happens on the bus all the time. And so that means that a stop could be empty. And so that gives us k to the n, so which is 6 to the 30. If, however, for some reason we required that someone gets off at least one person gets off at every stop, then it would be 6 factorial times the Stirling number of 30, comma 6. At each stop. Okay, that's our answer to the first one. A father has 15 different tasks to assign to his 3 children. In how many ways can he assign these tasks to the children, assuming that each child must be given at least one task? So again, talk with your neighbor. Or what's N, what's K? Are they distinguishable?
Yeah.
All right, what's N? N is number of tasks. What's K? 3 children. Are they distinguishable? Is N distinguishable? Is K distinguishable? I think so, because they're like, he has 3 distinct children. The children are different people. Okay, and so if the children are the boxes, so they're receiving some different number of tasks. Can a box be empty? No, each child has to have at least one task. So that gives us that criteria. And so this means we have 3 factorial times the Stirling number of 15, comma 3. Great. Here, let me bring this down here. All right. A PE teacher asks her class of 12 students to run a total of 40 laps around the track. In how many ways can the laps be allocated? Talk about it.
It doesn't say like it's like students to sort of think about. Oh, the student difference, yeah. Oh, right, it's these are all every single lap is a lap. It's like no issue, but every student is. And then they can't be 10 minutes. Is there anything that each student is not using?
Oh,
All right, what's N? 40? What's K? Is N distinguishable? Is K distinguishable? See? Yes, because they're children and children are people. So if K is our number of boxes, can a box be empty? Yeah, there's no requirement in the question, so a child may not be assigned a lap to run. So this falls under which quadrant? 1, 2, 3, and 4. Quadrant 3. So indistinguishable items, distinguishable boxes. Remember, A is for the non-empty case, B is for the empty case. And so this is C of 40 plus 12 minus 1. Choose 12 minus 1, which is equal to 52 minus 1 is 51. Choose 11. Right. All right, a father has 20 identical $1 bills that he wants to place into 4 unmarked envelopes, one for each of his 4 children. In how many ways can he distribute the bills if the envelopes must hold a different number of bills? Talk about it.
Or is, yes. Sorry.
They subtract the number of outcomes for their line. Right, sorry, I was thinking that was I think you have yeah, so those of them are. They're gonna be a lot.
Okay. What's N? Is it distinguishable? No. If we had some requirement about like the serial number, maybe. So not distinguishable. What's K? 4? Is it distinguishable?
Yeah.
What's your argument for yes?
Even though they're from marks, it has to be a different number of bills. In each envelope.
Yeah, no. Fun. Different number of bills? Yes, but that's a different complicating question. are the envelopes distinguishable or indistinguishable? So they're indistinguishable because it's not like he's giving money to his children directly, but he's putting them in envelopes that then will be distributed to his children. So they're both indistinguishable. This is a bit of a trick question where must hold a different number of bills. We don't really know how to get that. But so there's no requirement that could something be empty? I think so. And so then we would fall into quadrant 4. Probably part B. But that it's overcounting because we have to have a different number of bills in each envelope. Okay, so this was your trick question where I'm not going to ask something like this on the exam. But these questions can continue to get harder if we wanted them to. All right. So I will delete that. So we're out of time for today. Not tomorrow. Friday will be our review for the exam day. I'm aware that this is a stressful time in the semester for you and for me. So I want you to write your own exam. So go home, think of some questions relating to this chapter. So the chapter 11 that we've gone through. Go home, think some questions, bring them on Friday, and we'll talk about them, and I'm going to have you write your own exam. I will give you the caveat that the things that you write may not exactly correspond to the actual exam that you are given. I'll probably change some numbers, move it around. But the general format will be similar. Okay, several questions. Yes. As a class. Yep. No, I would give you that table. Question? Okay, and other questions? All right, thank you. Write your questions, bring them on Friday. Thank you for coming.